All right. Question one on the quiz. How much should a healthy Shetland pony weigh? Let X be the age of pony in months and let Y be the average weight of the pony in kilograms. So we'll click use salt. Okay. So what salt will do is it will upload the regression for you. So I'm going to do this where I can see all of them. So I'm going to go over to regression. Okay. In the X variable, put X age in months, and the Y, I'll put the average weight in kilograms. So notice that on this one, the smaller numbers, 4, 6, 8, those are on the X-axis. The larger numbers are on the Y-axis. It's got a positive correlation. Not that one. Didn't mean to click that. It's going to have a positive correlation, and the smaller numbers are on the X, and the bigger numbers on the Y. So like right there, that's what we want. Okay. So positive correlation. Sorry, smaller numbers on the X, bigger numbers on the Y. Now, how would you classify the correlation? So what I do on this is I go down here. I'm actually going to do part C first. I'm going to find the value of R. R is the correlation. So I'm going to copy this. And then how do I classify this? Well, first off, it is positive. Why do I know that? Because R is positive and because the association is positive. Now, how do I classify it? Low, moderate, or strong? The closer it is to 1 or the closer it is to -1, the stronger it is. And this is close to 1. We say anything above 0.8 is strong. So we'll say strong and positive. So as X increases from 3 to 21 months, does the value of R imply it should tend to increase or decrease? Well, since it's positive, as X increases, Y should tend to increase. So Y should tend to increase as X increases. So as X increases, Y will also increase. All right. Got him. All right. Let's look at number 2. An economist, I'm going to get out of this one here. An economist is studying the job market in Denver area neighborhoods. Let X represent the total number of jobs in a given neighborhood. Let Y represent the total number of entry-level jobs in the same neighborhood. Sample of 6 Denver neighborhoods gave the following information. So I'm going to click use salt. I'm going to pull this out. So this is going to be 9.2 right here. And so we're going to do a scatter plot first. So I'll click over to regression. Okay. So regression, my X variable, total number of jobs. Y variable, the number of entry-level jobs. So I'll look at the association. It is a positive association, and it looks like the bigger numbers on the X, the smaller numbers on the Y. So it's a positive association. So positive. Okay. So bigger numbers on the X. This is flip-flopped right there. So you see how the bigger numbers on the X, smaller on the Y. All right, find X bar and Y bar. So how do I find that? I'm going to go to descriptive statistics. X bar is the mean of the X's. So X bar is 34. Y bar is the mean of the Y's. So that's 4.1667. Find the equation of the line of best fit. For this, I go back to regression. So I'm going to go back to regression. How this works is I'm going to look at these coefficients. Okay. I'm going to start with the coefficient of the intercept, and they want me to go to 4 decimal places. So I'm going to start here. This is my y-intercept. So I'm going to put that first. Plus this right here, the coefficient of my x variable. Think about it like y equals mx plus b. The coefficient of x is the slope. This is my slope. So Control C, Control V times x. Okay. Graph the least squares line. So what I want to see on this line is I want to see a positive association, and I want to see the coordinate 34, 4.167 on there. So those are negative, positive. and 34, 4.67, so right there. Find the value of the coefficient of determination, that is r squared. So control C, or control C. So it's 0.6002. So what that means is that 60.02% of the variations explained by the model. What's unexplained, all you got to do is take 100% minus 60.02. So 39.98 is unexplained. So convert this to a percent, move it to the right 2 spots, and then do 100% minus that to get unexplained. For a neighborhood with 4,300 jobs, how many are predicted to be entry-level jobs? So for 43, I'm going to go plug in 43 into my equation I made. So I'm going to go 43 up here, negative 1.3889 plus 0.1634 times 43. 5.63, and I'm not sure how they want me to round. It's 2 decimal places, so 5.64. Oops. Okay. All right, let's go to number 3. Number 3 was 9.3. First thing I want to do on number 3, well, actually, let's just read the question. What is the optimal time a scuba diver to be on the bottom of the ocean? That depends on the depth of the dive. The U.S. Navy has done a lot of research on this topic. Navy defines optimal time as time for depth, the best balance, length of work, and decompression after surfing. Let X be the dive in meters and Y be the time in hours. So I'm going to, actually, I'll do that in a moment. First off, the level of significance of the test. So on this one, we're going to go to Greek, and we're going to select the row, and we assume that it's equal to 0. And now what we're trying to do is test a claim that's less than 0. So I'm going to go to Greek, select row, less than 0. Okay. So, all right. So video did not play there. So you go to, I did not show this. You go to stats, test. I entered it in my calculator. Lenreg t-test, L1, L2, less than, and then my t-value is negative 10.01. My p-value is really, really small. That's like 4 zeros in there, because you would move that over 5 spots to the left. Okay. So we reject the hoe. There's sufficient evidence that's less than 0. Now, I'm going to make an equation out of this. It gives you the parameters for the equation. So the A plus BX, A is 3.373 minus B, which is 0.055 times X. That's the equation. And I'm going to plug in 19 into that. Okay. 3.373 minus 0.055 times 19. 2.328. Okay, so 2.33. I didn't pay attention there. 2 spots. Now, this next one is really hard, and I did not go over this in the notes, so I'm going to try to give you kind of a crash course on how to do it. Some of us had the same questions, which is fine. But for this one, we've got to find an 80% confidence interval for when X is 19. So how do you do that? It's the Y hat plus or minus the error. Now, the error is this long formula here. Y hat is this right there, okay? So first off, this gets kind of complicated. I got to find the critical value for t. And the critical value, to find the critical value, I've got to know the degrees of freedom. The degrees of freedom for this section is n minus 2. So I had, how many in my sample? I had 7. So it'd be 7 minus 2, so it's 5. So my degrees of freedom is 5. Now, what you're going to do is you're going to visualize this, an 80% confidence interval. You want to know what the value of t is at this high fence area. So think about this, 8%'s in there, 10%'s here, 10%'s here. So I got to first give me the area. When I go to inverse t, I've got to give them the area. Second bars is how I get there. Bars is right there. Inverse t, the area is what's at this point and below. So what's at this point and below? 80 plus 10, which is 90%, which is 0.9, and degrees of freedom is 5. So inverse t, 0.95, and you want to go, I'll just go 3 spots. 1.476. All right, so now what I'm going to have to do next, this gets a little complicated, and I apologize. So the error is equal to the critical value, which is 1.476, times the standard error. I've got to go up here to find that. Standard error. Standard error is right there, 0.1678. Did this wrong yesterday trying to do this. So it's 1 minus 1 divided by n plus n is 7. Now, x, all right, so now x is the value of the, x is going to be the value of this thing here, what they give us, was it, 19, minus the mean of the x. Mean of the x, I don't know the mean of the x. I've got to go find it. So I've got to go to, actually I can do that in my calculator, stats, calc, 1 bar stats, 28.771. Apologize for that. So I went to stat, calc, 1 bar stats, and it's the mean there. Okay. I didn't go over this in the notes, so that don't feel bad about this. Now, n is 7. E to the x squared is the sum of the x squareds. That's up here somewhere. 6,735.46 minus the sum of the x's squared. So 201.4 squared. Okay. So that's not much fun, I know. All right, that gives me the error. That's not going to give me my answer, but that's going to help me get the answer. 1678 times the square root of 1 minus 1 divided by 7 plus, and I'm going to do open parentheses, 7 times 19 minus 28.771 squared, close parentheses, divided by 7 times 6,735.46. Okay, that's going to be minus 201.4 squared. 0.24, I hope this is right because it's a little stressful. 0.242 is my margin of error. So now what I'm going to do is I'm going to take my predicted value, 2.33, and I'm going to add and subtract 0.242. So 2.33 minus 0.242, 2.08, and this is actually a little off. Okay, this is actually a little off. So there's something off somewhere. So it should be 2.06 to 2.61. So it looks like I typed something wrong in there somewhere, and I don't really have time to look into it.
Crazy. That is crazy.
All right. So 2.06. Okay. The only problem with this, I did not teach that, but I had to add that to be able to do this problem. Use a 1% level of significance to test the claim that beta is less than 0. So my I'm going to go to Greek. Beta equals 0. And what am I trying to prove? Greek beta is less than 0. All right, so now next I'm going to go do the same thing, linear regression t-test. So it will give you the same statistic as A, because doing this a test for the slope and the correlation is going to give you the same one. So it's going to give you the same answers. Yes, that, and it's going to be less than. And that's a very small p-value. You put 4 zeros in front of that, and then 8.5. Now, on this one, we're going to reject Ho because it's a small p-value, so we have sufficient evidence to claim that the slope is less than 0. Now, to do a 90% confidence interval for this one, I'm going to go to stat test linreg t-interval for a confidence interval. L1, L2, 90%, 0.9, and it gives me that. So, what do we go? 3 decimal places, negative 0.066 to negative 0.044. What can we say? We could say that 90% confident that it falls within the interval, that for every 1 meter increase in depth, the optimal time falls within the interval. Okay. So that's our 90% confidence interval. All right. Let me submit that. Okay. Negative 0.044. All right, let's go to number 4. Okay, which of the following, use the following linear regression equation to answer the questions. Which one's the response variable? The response is what it's equal to, so it'd be x1. The explanatory variables are on the other side. So these are like your x's. So multiple regression, we have multiple variables, multiple explanatory variables. So x2, x3, x4. What's the constant in the term? The constant is the term that does not have a variable attached to it. That's 1.3. List the coefficients of their corresponding explanatory variables. Okay. So x2 has an explanatory variable of 3.4. I'm going to copy this equation now because I'm going to need this here in a moment. So I'm going to copy this down. X1 equals 1.3 plus 3.4 x2 minus 8.1 x3 plus 1.6 x4. So my coefficient of x2 is 3.4. My coefficient of x3 is negative 8.1. My coefficient of x4 is 1.6. Now, on C, they asked me to plug in if x2 equals 3, x3 equals 6, and x4 equals 8, what's the predicted value for x1? I'm going to plug in those x2, x3, and x4 values. 1 times 6 plus 1.6 times 8. Okay, so I'll just plug those in, type that in my calculator. 1.3, whoops, didn't mean to do negative. 1.3 plus 3.4 times 3 minus 8.1 times 6 plus 1.6 times 8. Got negative 24.3 there. Sorry about that, negative 24.3. Okay. Now, explain how each coefficient can be thought of as a slope. So if we basically on this one, if we hold all the other explanatory variables as fixed constants, so we had fixed all the variables, then we could look at, it's this one right here, then we could look at one coefficient as a slope. Okay. All right. Okay. All right. Now, let's go to, suppose x3 and x4 were held at fixed, but their arbitrary values and arbitrary values, and x2 increased by 1 unit. What would be the corresponding change in x1? So what happens if we fix x3 and x4? We fix that and we change this. So if we change it by, increase it by 1 unit, it would be that slope times the number of times it's changed. So 3.1 times 4 3.1. Okay, you can try it out there. So 3.4. Now, if you were to increase the value of x2 by 2, so that means x2 be increased by 2, you take 3.4 times 2, and you would get 6.8. So 6.8 would be your value there. What if you decrease it by 4? So decreasing it by 4 means it'd be multiplied by negative 4. So 3.4 times negative 4, negative 13.6. Okay. Now, suppose that n equals 18 data points were used to construct the given regression equation, and the standard error for the coefficient is 3.14. Construct a 90% confidence interval for x2. So this would, to do the confidence interval, what you're going to have to do first off is, let's go ahead and write down the formula. It's basically the slope of that, which in this case is x2, so I'll call it b2, plus or minus the critical value of t times the standard error. Okay, let's talk about this. b2 is the slope of 2, which is 3.4, so b2 is 3.4. The critical value, well, first off, we have to know the degrees of freedom to know the critical value, and this is multiple regression. So here's how degrees of freedom work for multiple regression. It's n minus k minus 1. K is the number of explanatory variables. Okay, so what does that mean? The number of, in this case, I have 3 explanatory variables. I'll show you. So the number of explanatory variables, these 3. So it would be n, which is my sample size, which is 18, minus 3, minus 1. So it would be 14. Now to find the critical value, I go to inverse t. Okay, and let's kind of visualize this. It's a 90% confidence interval. I want to know the t at the high end. So 5%'s here, 5%'s here. The t at the high end, the area is what's at that point below. So what area is at that point below? 95%. Good. 95%, which we'll convert to a number, 0.95. So it'd be inverse t, 0.95 and 14. You can go to second bars to get inverse t. So second bars, inverse t, 0.95, 14, 1.761. Okay, and that's not my answer. That's going to give me the critical value. Okay, I'm closer though. So now my slope, B2, is 3.4, plus or minus my critical value, which is 1.761, times the standard error, which is 0.314. And so I need to multiply those together and then add, subtract it from 3.4. So 1.761 times 0.314, 0.553. So 3.4 plus or minus 0.553. 3.4 minus 0.553. 3.4 plus 0.553. And so it should be 2.85 to 3.95. Okay. Sorry, move this up. So 2.85 to 3.95. Now we're going to do a hypothesis test, okay, to declare the coefficients different from 0. To do a hypothesis test, we're going to need beta again. Now, but we're doing the second one, so we're going to do beta. So beta is like the real slope for that second variable. So I'm going to go to Greek, beta, and I'm going to go to functions and do the subscript. So beta of 2, because it's the second one, and I assume it equals 0. What am I trying to prove? Beta sub 2, okay, is different from 0. So beta sub 2 is different. So that's exclamation point equals 0. Okay. Now, the sampling, the test statistic on this one, we have to do it by hand. How do you do the test statistic? It's the value of the slope minus the hypothesized value of the slope, which is beta 2, divided by the standard error. Okay. Now, the slope value is 3.4. Beta 2 is the hypothesized value. That's 0, so it's going to be minus 0. You could just leave that off if you want. Divided by the standard error, which is up here somewhere, 0.314. So it'd be 3.4 divided by 0.314. 10.83. Now, this is going to produce a very small p-value. How do I get the p-value? So I'm going to draw a t-distribution. 0's in the middle. 10.83 is up here. Now, here's the problem, though. This is a two-tailed test because it's different. So I've also got to find the area below the negative of that. So how do I find the area? I do TCDF. .83. Upper value, 100. Degrees of freedom, it is 14. So 10.83, 114. And then I'm going to multiply this by 2 because that was just one of the areas. So I'm going to multiply by. Now, that's a very small p-value. That's like 7 zeros in front of that. And so if I multiply that 2, it's still going to be a very small p-value. Okay, it's like 7 zeros and then 3. So it's going to be less than 0.01. So what's my conclusion going to be? I'm going to reject the null hypothesis. I'm going to say there's sufficient evidence because when p is low, we reject HO. And this is a very low p. We'll reject HO and say that it differs from 0. And so if we conclude it's not different from 0, we would remove that variable from the model, and that would be x2. Yeah. Okay. All right. Make sure this all went through all right. All right.